Welcome to The Explainer. I'm so thrilled you're here today because we are going to unravel a fascinating piece of everyday engineering that is hiding right in plain sight. We're talking about something millions of people sit underneath every single day without ever truly understanding how it works. And you know what? I'm actually going to skip our usual agenda today because I really want to preserve the big surprise we've got in store for you. Okay, let's dive into this. Picture it. You're sitting on a commercial airliner, 35,000 feet up in the air. The flight attendant is going through the standard safety briefing, and they mention that in the event of a loss of cabin pressure, an oxygen mask will drop from the panel above your head. Now, most of us instinctively imagine that the airplane is flying around with massive scuba tanks hidden up in the ceiling or maybe down in the belly of the plane, just waiting to pump fresh air through this huge network of pipes. But is that actually the reality? Section 1. The Hidden Oxygen Myth. To get to the truth, we first need to look at why our assumptions about passenger safety are, well, fundamentally flawed. The myth is simple, right? And it makes total logical sense if you're not from aviation. You breathe gas, therefore the plane must store gas. But let's think about this from an engineering standpoint. Imagine a large jetliner carrying upwards of 435 passengers. If you had to supply every single one of them with pressurized gaseous oxygen for just 30 minutes, you would need at least 40 meters of high-pressure piping running the entire length of the aircraft ceiling. It would be an absolute logistical nightmare. We're talking constant maintenance, pressure checks, temperature monitoring, the whole shebang. And this brilliantly illustrates the contrast. On one side, you have a heavy, solid metal cylinder that's required to safely hold pressurized gaseous aviators breathing oxygen. On the other side, we have this incredibly lightweight, flexible, simple passenger mask that actually drops down. Commercial airlines need a solution that fits directly above your head, takes up literally almost no space, requires basically zero maintenance for years on end, and weighs a mere fraction of a steel cylinder. So if there are no tanks up there, what exactly is hiding in this ceiling? Section 2. How chemical oxygen works. The astonishing reality of aviation engineering is that we don't actually store the oxygen for passengers. We literally make it right there on the spot the exact moment you need it. Stashed above your seat is a marvel of modern chemistry called a chemical oxygen generator. In the industry, it's also informally known as an oxygen candle. This device produces breathable oxygen instantaneously through a carefully controlled chemical reaction. And while it might sound like some futuristic sci-fi tech, this sodium chlorate chemistry has actually been commercially proven for decades. Fact is, it's been used to generate breathable oxygen in submarines since the early 1900s. So here's exactly what happens when those masks drop. You've heard the instruction, right? Pull the mask towards you to start the flow of oxygen. Well, that tug isn't just opening a valve. When you pull that lanyard pin, you're actually triggering a mechanical strike. It's literally just like striking a match. This phosphate match creates a highly localized, intense heat source inside the generator. That heat then ignites a core made of sodium chlorate and iron. As these chemicals burn, the thermal degradation immediately produces pure, breathable oxygen gas as a byproduct, and that flows right into your mask. But here's an absolutely critical detail about this chemistry. Once that reaction is initiated, there's no going back. It cannot be stopped. It is strictly a single-use process. The carefully calculated concentrations of iron and sodium chlorate guarantee that the prescribed amount of oxygen is delivered at a completely constant rate until the chemical fuel is entirely spent. You can't turn it off, and you definitely can't pause it. Now, this chemical reaction burns extremely hot. We're talking hundreds of degrees inside that little ceiling compartment. And this leads to a very common and very understandable passenger panic. During an emergency depressurization, passengers will often report a terrifying burning smell. But if you know how this works, you know it's actually a sign of safety. That smell is usually just accumulated dust burning off the extremely hot exterior of the canisters up in the ceiling panels. Alternatively, it can sometimes be engine bleed air pulled into the aircraft's air conditioning packs. Either way, that intense heat and faint burning smell, it just means your life-saving oxygen candle is doing exactly what it was designed to do. Section 3. Why not pure oxygen? So even if chemical oxygen is undeniably cool, you might be wondering, why not just bite the bullet and use traditional pure oxygen tanks like they use in hospitals? Well, when we compare the two sources side by side, the answer becomes pretty obvious. Stored gaseous oxygen is incredibly heavy. It's bulky, and it requires a complex delivery system of pipes that are super vulnerable to breaking. Airlines would have to constantly monitor tank temperatures and pressures and refill them all the time. Chemical generators, on the other hand, are completely self-contained modules. They're lightweight, they're cheap, and they can literally sit unbothered in a stowage compartment for years without ever needing to be topped up or intensely maintained. But beyond cost and maintenance, there's a massive safety factor at play here. To quote a contributor from the Aviation Stack Exchange, pressurized oxygen tanks are essentially a small bomb. Having dozens of highly pressurized tanks of pure oxygen spread throughout a passenger cabin introduces a severe explosive hazard. If there were ever an onboard fire or if the aircraft sustained structural damage, those high-pressure pure oxygen tanks would be totally catastrophic. Chemical generators, sure, they get hot, but they are far less volatile to store over thousands and thousands of flights. So the crucial point is weight. Remember those 435 passengers we talked about earlier? Well, if you had to carry enough gaseous tank oxygen to supply them for a 30-minute emergency, you'd be adding an estimated 1 entire ton of dead load to the aircraft. For an airline trying to maximize fuel efficiency and payload, dragging a ton of heavy steel cylinders around the sky for an emergency that will likely never happen, it simply isn't feasible when a lightweight chemical alternative already exists. Section 4, Inside the Passenger Mask. Let's zoom in on the actual hardware you'll be strapping to your face. Now, what's really interesting about this slide is the specific design. Notice the bright yellow silicone facepiece that's specifically designed for immediate identification during the sheer chaos of an emergency. Attached to it is a clear plastic reservoir bag and a highly specific set of circular valves. This isn't just a simple cup, guys. It's a continuous flow phase dilution mask. Here is the sequential genius of this phase dilution system. Remember, the chemical generator provides a continuous, unstoppable flow of oxygen. That metered oxygen flows down the tube and fills that clear reservoir bag while you're exhaling. When you breathe in, a one-way valve lets you rapidly draw that pure oxygen directly from the bag. But what if you panic and breathe so deeply that you completely empty the bag before your breath is finished? Well, a second spring-loaded ambient valve on the mask automatically opens up, allowing ambient cabin air to mix in so you can still take a full breath. Finally, when you breathe out, an exhalation valve safely pushes your breath out into the cabin. This ensures your exhaled carbon dioxide never goes back into the pure oxygen reservoir bag. This ingenious mixing of pure oxygen and cabin air keeps you physiologically safe at altitudes up to 40,000 feet. And we really have to address a terrifying misconception here. The safety briefing always says even though oxygen is flowing, the bag may not inflate. Because of how rapidly passengers breathe during an emergency, and because the valve system is so efficient at letting you suck the oxygen right out, the bag will often appear totally flat. If you don't know this, you might honestly think your mask is broken and start to panic. But rest assured, if you gave that lanyard a tug and pulled the pin, the chemical reaction is happening and life-saving oxygen is flowing directly to you. Section 5, the 15-minute lifeline. Okay, so we've seen how the oxygen is made and how the mask delivers it, but we need to talk about what is arguably the most alarming limitation of this entire system: 12 to 20 minutes. That is the entire lifespan of the chemical oxygen generator. Once you pull that pin, that burning core of sodium chlorate will completely exhaust itself in less than 20 minutes. For many people, hearing this induces immediate panic. If a flight is hours long, how can 20 minutes of oxygen possibly be enough to save us? Well, here is where the wider picture of aviation safety comes in to save the day. The oxygen masks aren't there to sustain you for the rest of the flight. They're just a temporary bridge. In the event of depressurization, a commercial airliner can execute an emergency descent at an astonishing rate of around 8,000 feet per minute. The primary goal is to get the aircraft down to 10,000 feet, which is an altitude where the outside air is thick enough for humans to breathe normally without masks. If you're cruising at 38,000 feet, it will take the pilots less than 5 minutes to safely dive down to that breathable altitude. Therefore, 12 to 20 minutes of chemical oxygen is more than enough time to keep you conscious and perfectly safe during that rapid descent. But while you, the passenger, only need a temporary bridge, the pilots are a totally different story. The cockpit utilizes a completely separate system. Because pilots have to maintain absolute mental clarity to aviate, navigate, and communicate, often while troubleshooting some pretty complex emergencies, they cannot rely on a short-lived chemical candle. The flight deck is equipped with those heavy, pressurized, gaseous oxygen tanks we talked about earlier. Their quick-donning masks supply positive pressure oxygen for up to 2 hours. And unlike our passenger system, pilots can actually turn their flow on and off as needed. Aviation engineers gladly take on the weight penalty for the cockpit because, at the end of the day, the pilots are the ones who have to safely land the plane. It truly is a masterclass in risk management, balancing weight, chemistry, and human physiology to keep us all safe up in the skies. So I'll leave you with this. Next time you're settling into your window seat and the flight attendant points up to the ceiling, will you ever look at that little plastic panel the same way again? because you now know that right above your head sits a dormant, perfectly calculated chemical reaction, just waiting for the pull of a pin to spark to life. Thank you so much for joining me for this explainer. Keep asking questions, and I'll see you next time as we uncover more fascinating truths hidden right in plain sight.